All right, so oh, you know what? There's one other thing I need to check on sharing screen real quick. Right. Okay, so you want to go to the infiltration and soil moisture page, and then there are two versions of this spreadsheet. It says Green Amp Method Hornberger version. That's Green Amp F20 without TP. I'll explain what all it is. You want to download that and have it handy. And we may not get very far with this one, but the Green Amp method, Dingman method, Green Amp F20 with TP clean. So I'll explain why there are two versions of that in there and what we're doing with them as we go along. We're not going to start there, but we will make our way there before long. So before we do that, there's some background. We're going to kind of pick up where we left off last time, and I'll just remind you of something I said last time because it's germane to what we're going to do both now and developing some what we're going to do now, and that is that I talked last time about the part of the issue with moisture in the unsaturated zone was also that we think of soil as the gatekeeper for water that may infiltrate into the subsurface, may eventually become groundwater, may be evaporated, or may become surface runoff. And so to the extent that properties of the soil or conditions, antecedent conditions and moisture conditions affecting the transfer of moisture into the soil also can determine whether moisture does not get into the soil and winds up running off. So in fact, infiltration and soil moisture understanding is critical to understanding what actually generates runoff. And so, you know, we have talked about stream flow, we've talked about discharge, we've talked about hydrographs, we've talked about other things at the watershed scale, but the topic that will be coming up next after this chapter is how runoff gets generated in the landscape. And that is very much influenced by this aspect of the hydrologic cycle here, which is why we do this first before we talk about how runoff gets generated. So you'll remember that we have talked at length about hydraulic head. We've talked about the component of head that's a pressure head, that's positive pressure beneath the water table. And then we introduced this concept of, in the unsaturated zone, we have sort of the inverse, where we have negative head. We have tension head, water that's being held in pores by surface tension. And so I'm just going to, even though I showed this last time, I'm going to start here and then move forward. So we talked about piezometers, right? Piezometer is basically the equivalent of like an observation well. It's not open through its entire depth, but just at one location, because what it's doing is measuring the head at that location, and the height to which the water level rises in the piezometer tells you what the pressure head plus the elevation head was, the elevation of the observation point plus the pressure head that raises the water level to some point above that. If you have those kinds of observations, you can use those both to compare. Therese, nice to see you. Come on in, have a seat. You know, so if you have those observation points, you can both, if you have enough of them, you can map the distribution of head. We talked about things like, you know, piezometer nests for getting different heads at different depths at the same location, and you can track changes over time. Well, the corollary to that, or the other case similar to that, is when you're dealing with water in the unsaturated zone, you can put tensiometers in the soil, because the tensiometer also is measuring head, but it's measuring negative head, right? So you've got this porous cup that's at the end of this tube, and the porous cup sits in the soil, and because there is a tension force pulling water from the water in the tube across the boundary and into the soil, it will equilibrate to the point where the internal tension head is the same as what's in the soil. That gets measured on a pressure gauge. So just the same way that a piezometer that's got a water level recorder can keep track of changes in the hydraulic head beneath the water table, a tensiometer can keep track of changes that are induced by changes in the tension head over time as well, as the soil either dries out or wets up a little bit. So I mention that because you don't have these everywhere. And so a lot of work is done modeling these processes. And so you want to know that at least in some places that you've got data that's been collected from real measurements that you can compare to see whether the model is actually simulating and matches up fairly well with observations. There's one example that we're going to do, we'll point out that's in the textbook today, using this green amp method I talked about, where it shows that they came up with a pretty good match. So I'm not going to go over this again. We did this last time, but this was just for the case where you have no net flow in either direction. And so I think we did a derivation, and I'm not going to repeat, where you found that if you take the one-dimensional form of the Richards equation and say that it's steady flow rather than unsteady flow, you can solve for it and find that the tension head is equal to negative z being the elevation head, and you get a kind of a straight line relationship there. With this point here at the water table being where tension head is 0, we typically say the tension head is 0 at the water table. We'll say more about that in the next slide. So this is the only new slide you've seen so far. And this actually is from the Dingman textbook. And it's actually a very good slide for kind of putting a lot of things in perspective that we've been talking about. So for starters, there are different zones in here, right? There's not actually a distance scale on here. So here's the root zone, right? And you've got plants that are sucking moisture out of the soil. And so there's ET going on that's causing them to pull moisture up and out of the soil. So then you've got an intermediate zone here. Then you've got what they call a tension saturated zone, water table, groundwater, and impermeable layer. Now, if you look at the scale, you'd think, oh, that's a pretty narrow aquifer. It's no deeper than the root zone. There's nothing, that's not the scale, right? That's just showing you conceptually what these different regions are. But to go along with this is what you see here. So this is what they're calling the pressure state. This figure is from the Dingman textbook. So when you have positive pressure, then you're beneath the water table, right? So at the water table, again, what's the pressure at the water table?
Should be 0, right?
Should be 0, right? I mean, it's not actually 0, right? It's atmospheric pressure, but we basically set it equal to 0. We call that gauge pressure, and our datum is 0 because we're trying to exclude the effect of the atmosphere here. So 0 pressure here, positive pressure here. We all know that the pressure head is a function of the depth below. Well, it varies once you're actually dealing in a real aquifer, but if you're having in a column of water, certainly the pressure head is just direct function of the depth. And then above the water table, you know that you have this narrow zone where, because of the tension that is exerted by the pores pulling water into them, you actually have this capillary fringe, the zone where the pores are all filled with water, but they are not causing positive pressure because they're actually being held in those pores by tension. So, in fact, right at this location, Dingman makes the point that you have a tension head equal to what he calls the air entry tension. So that will vary by soil, but essentially it's just the moisture that gets pulled up, very much like, wicking into a narrow tube, a capillary tube, and the size of the tube affects that and all the rest of that. But the main point here is that this is on the negative side, but what you find is that as you go up from here, various factors affecting what's going on in the soil influence what the head tends to be. Certainly there is downward transport of water that takes place within this profile, but the main thing we're seeing here is that there is a gradual decrease in the soil moisture content, even if you're not in the soil, even if you're down below the soil. But there's a decrease in the moisture content, and then there's also an increase in the negative pressure or in the tension head as the soil dries out. And I mean, if you have a hot summer, not a lot of rain, and soil really dries out, the tension head gets strong enough, what can happen? This relates to something we talked about with regard to, remember we talked about available moisture in the soil, right? The difference between field capacity and what?
The wilting point.
Permanent wilting point, right? So The reason why there is a wilting point is because there is some amount of suction that's greater than what the plants are able to exert in order to pull more moisture out of the soil, at which point they wilt because they can't get the moisture they need, right? So somewhere up here, that's a possibility, although it's not automatic in terms of what's in this figure. So this figure sort of helps to put a bunch of things in perspective for what we're going to be talking about, which is really the dynamics of how this moisture is moving through the unsaturated zone. We'll talk a little bit about measuring infiltration here. Let me just go to this picture first. This is also from Dingman, and it's basically, this thing is called an infiltrometer. In fact, this one's a double ring. I'll explain why there's such a thing as a double ring in a moment. But the basic idea of an infiltrometer is that you have this cylinder, you put it into the ground, you pour water into it, and you try to maintain a constant head, a constant water level at above the soil surface, and then you basically figure out how much water you have to keep adding in order to maintain the water at that same level, and that becomes a measure of the rate of infiltration into the soil because that water is seeping down into the subsurface, right? Now, the thing that's interesting about this is if you're seeking to measure the rate of infiltration, thinking in a one-dimensional fashion about the vertical transfer downward, what's the problem here? How is this going to perhaps frustrate your expectations of getting a good measure of vertical downward transport?
You have horizontal transport.
Yeah, horizontal transport. Why?
Because it's going against the equipotential lines. It's going to flow out and back up.
Okay, well, these are not actually equipotential lines. This is actually, these are just, basically, if you think of the wetting front, that's time 1, time 2, time 3, and time 4. Although the flow does go perpendicular to equipotential lines, there are equipotential lines in there somewhere. But the main thing is, why is it spreading out this way? And we talked about the one-dimensional Richards equation, and we talked only about the vertical dimension, right? So what? Yes, Dan.
Maybe the porosity of ground, or like what the material is made of.
Well, I'm gonna make it impossible to give that answer so I can move in the direction I want to move in. Okay. So if you get me, that's a plausible answer. But let's assume we have homogeneous material and that it's not a function of differences in the soil itself. Liza.
I mean, it's literally just drier on the outsides, and the water is going to go.
Right. So the water will go down a gradient, right? It'll go from, it'll go from higher moisture content to lower moisture content. And so this is a flawed experiment, right? Because if I try to wet this and watch what's going on here, and it's drier on either side, then the moisture is going to go out in the direction. I'm basically feeding the soil around me. I'm not strictly measuring what's below me. Here comes the double ring infiltrometer as a partial solution to that problem, because what you do is you pour water on the outside, but you also maintain constant head in the inside. And the idea is that this creates an environment where there's already moisture in the soil surrounding the zone where you're actually measuring in the inner ring, right? So it's just a device that's intended to give you a situation where what's beneath that inner ring will not be so much affected by these moisture gradients. There's still going to be a moisture gradient, but it won't be as much effect on that narrow central region, right? Okay, so just a few figures that talk about the downward transport of moisture, and they're actually measuring a few different things. Because there's not as much about this, about observational data in the Hornberger textbook, even though I love the Hornberger textbook for its explanations. That's why you see a lot of examples from Dingman. So this is actually not soil moisture depth, okay? This is basically infiltration rates for 4 different water input rates. So some kind of sprinkling experiment was carried out. And over here, you're actually going to see the downward transport of moisture within the unsaturated zone. But here, you're just looking at the infiltration rates. What they're showing you is really 2 things. Number one, the infiltration rates, these black dots, are for the lowest application rate. Now, the lowest application rate is 78 millimeters per hour. That's more than 3 inches per hour. That's pretty unusual. We do not get 3 inches per hour in an average year around here. We might get it every couple of years. So that's a very high rain rate, and these others are astronomical. But even so, what you're seeing is that actually you're getting higher infiltration rates with higher application rates, but you're also seeing that in the initial early going, the rates are fairly high and they decline and they kind of straighten out and become asymptotic to some final value. Now, the weird thing here is that if this is all the same soil, you wouldn't think they'd become asymptotic to different values. So actually, I'd have to go back and look at more about what this study actually showed to be able to interpret that. Because we're going to look at other evidence that suggests that over time, as you add water, the infiltration rate changes, and it usually does approach asymptotically some final value, which is often the saturated hydraulic conductivity of that layer itself. There doesn't appear to be one saturated hydraulic conductivity in here. This seems to be responding to the application rate. Now, if you look at the figure on the right, you're looking at different time steps following says during steady infiltration with no ponding. So let's just talk about what no ponding means for a moment. So if you want to know what no ponding means, you first have to start to think about, well, what does ponding mean in soil?
Puddles? I just thought.
Puddles, okay, but so suppose you've got an infiltration experiment going on, right? When ponding occurs, it's essentially telling you that what's happening. So water is accumulating at the surface, it can't get in. The soil may or may not be completely saturated, but the water is arriving at the surface faster than it can seep into the ground. And so you do get ponding, and that's actually an important distinction because when we look at the methods for predicting this, the question of whether you got ponding at the surface turns out to be an important one in terms of which methods you can apply. So what they're saying here is that it has no ponding, which means that, so this is water content. It's between about 23% and about 50%, and 50% is usually, if you got 50%, you're probably saturated in most soils. So this might be saturation at the surface, but yet it's not so saturated that it can't have water infiltrate. There's no ponding. But what we do know is that at some time after the beginning of infiltration, the wetting front, this is just showing that the wetting front in this soil that is actually at the surface here, it's a little bit low over here, and you could kind of imagine this as being more or less average it as a flat surface. The methods we're going to use are actually going to assume that you have a horizontal wetting front, and that it behaves as what we call plug flow, which is basically that there's a sharp boundary, it all moves down at once. This shows that there's actually some dispersion, so that some of it is shallower, some of it is deeper, depending on where you are. You might remember the experimental images I showed you last time that showed there's all kinds of other stuff going on. There could be macropores, you get water that bypasses a zone, and then water gets hung up at different places. So the real soil is always more complex than anything we simulate, but the real world is always more complex than anything we can simulate. You know, we just don't have the ability to capture all that information. We can't even get the data. So the question is, can we do approximate methods that actually capture important enough aspects to be reasonably useful for prediction purposes? So what they're showing you here is that's after 0.83 hour. This is after 8.3 hours. You see it's even more spread out, but it's also moving downward. And then after 83 hours, it's moved farther downward, and it's also more dispersed over a broader range of depths. So that suggests that the wetting front actually is going to tend to broaden and not necessarily be a straight flat surface. And yet I'll show you other findings that suggest that you could still get away with assuming it's a flat surface and make reasonably good predictions. So this is just from an old textbook, the Dunn and Leopold textbook we've talked about before. And it's just comparing infiltration capacity versus time in different kinds of soil conditions. So just for example, you already know that texture makes a difference in terms of how fast water moves in the soil, right? So, or in an aquifer, right? So coarser versus finer grained materials, which is going to have the higher hydraulic conductivity and which is going to transmit water more rapidly. Coarser, right? So this is a coarse textured gravelly sandy loam. That is a fine textured clay soil rich in colloids. And notice that they both start out higher than where they wind up. So that's going to be a theme we're going to keep seeing, that your initial infiltration rate is much higher, and then it slows down, levels out, and approaches some kind of asymptotic approximation of some final value, which may indeed be the saturated hydraulic conductivity in many cases. Here you have the clay soil. It's pretty obvious that that comes down pretty close to zero compared to the gravel and the sand. Now, these others have more to do with land cover and land management. So over here, you have good grazing management and poor grazing management. So what's that about? What's good grazing management versus poor grazing management? How does that affect infiltration capacity of the soil? Anybody?
It has to do, so if they have poor grazing management, then they're not like taking care of the plants on the surface. So like this, like the surface of the soil is like a different like composition.
Okay.
Basically. So you have like less roots, you have less like healthy vegetation to like intercept, so it's going to like hit the ground, and I think also the ground will get compacted more, so it won't be able to infiltrate as easily.
So what you've just said is a pretty good representation of several of these other graphs too. So here you see 4 plots, average vegetation density of 37%, 18%, bare plots, and you see a marked reduction when you don't have active vegetation growing and creating, roots actually create opening. I'm sorry?
It's the Dust Bowl issue.
I don't even want to get into the Dust Bowl because there's so many issues with that. We could spend the whole day on it. But yes, if you take the vegetation away, it has a lot of other consequences. Although when you have a drought, that's also, it's not only the removal of vegetation, it's also the drought that affected that. But
Did we watch a documentary on the Dust Bowl back in?
there are many documentaries about the Dust
I
Bowl.
thought we were
Wait, what
assigned
is
one in
it?
physical geo.
What's that?
I thought we were assigned one in physical geo back in spring. It might have been human geography.
Well, I wasn't teaching that one, so I don't know who was assigning it. Who did you take it with?
I had you for physical geography.
Not in the spring, you didn't, unless it
Spring
was a spring.
2021.
Oh. I don't think that I showed a documentary about the
Okay,
Dust
it
Bowl.
might have been a different class.
Yeah. Might have been in 120, I don't know.
Okay.
What is the dust?
The Dust Bowl?
Yeah, what is that issue?
So the Dust Bowl is basically,
Oh,
Um,
Dust Bowl.
Dust
I
Bowl,
said Dust Bowl. I was like, wait,
right.
like, I didn't know.
You ever
sounds
read
were
or see the
affected.
movie of, now I'm drawing a blank. Grapes of Wrath. Ever hear the
Yeah.
Grapes of Wrath? Yeah, that's what the Dust Bowl is
Okay,
about.
Dust
Woody
Bowl.
Guthrie,
Oh, okay.
Anyway, so that difference in vegetation cover makes a difference. Here you see pine forested land versus bare abandoned land. So the lack of roots and so forth is important. When you talk about grazing management, in addition to changes in the vegetation, cattle are very large and heavy animals. And if you put too many of them on a plot of land, they do indeed compact the soil. When they compact the soil, you lose a lot of the porosity, and you lose therefore a lot of the, you lose a lot, and the pores become smaller. You lose a lot of the hydraulic conductivity or the infiltration capacity as well. So poorly managed agricultural land often has much higher runoff rates, just like poorly managed urban land or impervious cover has very low infiltration rates, very high runoff rates. So keep these things in mind, because we're going to see when you model things that you actually can simulate this kind of behavior over time on a given soil. Now, this figure here also makes the same point I was making before about the soil acting as the gatekeeper. This is an artificial storm of constant intensity, 4.2 centimeters per hour, which again is a very high rain rate, close to 2 inches per hour. And so basically what they're showing is that if you put more rain on the ground than the ground can absorb in that time frame, you get to a point where you will get ponding on the surface, and then you'll see the infiltration capacity go down. And once the infiltration capacity is less than the rain rate, what happens to the water that can't infiltrate? It accumulates on the surface, it runs off. And so what they're basically doing here is they're subtracting the infiltration capacity from the rainfall rate, and they're getting a runoff rate. And so you're seeing, as this comes down, this goes up, and you get a large fraction of this rainfall becoming runoff. Rain ends, and then it drains off. And so these are sort of some fundamental relationships that illustrate why some of this stuff is important. We're not going to go to that right now. We'll probably look at that on Monday. So we're going to talk about infiltration capacity, and then we're going to work our way towards generating the green amped method for simulating this. And that's where you're going to need those spreadsheets I told you to download. So we're not there yet, but we will be there not too long from now. So were you here when I said that, or did you come in afterwards? Okay. So everybody knows what I'm talking about. Those 2 spreadsheets on the infiltration. Amal, did you miss that?
I missed that.
Okay, so if you go here, go to the infiltration, what is it called? Infiltration and soil moisture. You'd think I'd remember, right? Whoops, that's not what I wanted to do. Yeah, infiltration and soil moisture page, scroll down, and you'll see two spreadsheets, the Green Amp Method Hornberger version, the Green Amp Method Dingman version. I'll explain why I'm having you open two different versions. We're going to deal with this one first. If we run on the same time track as we did this morning, we will not get very far with this one, and we'll have to do it more on Monday. But there's a reason why I'm showing them both to you, and I'll explain that as we go along. But the main thing is download them and have them handy so that when I start to talk about them, you can open up and follow in what I'm doing so you can see how to develop these relationships. Okay. All right, so back to here. This is not where we were. We are here. Okay. The maximum infiltration, and this is text I took right out of the Hornberger textbook, but I parsed it into shorter sections so that we can walk through what they're really saying. You know, I think that this book is quite well written, and although it's not as comprehensive as Dingman and perhaps some other engineering hydrology textbooks, I think its strength is the quality of its explanations. So I'm going to go literally from the source. So the maximum infiltration rate, commonly called infiltration capacity of a soil, is the rate at which water will move vertically downward when a supply of water at zero pressure is maintained at the surface. At zero pressure is code for that's saturated at the surface, right? The infiltration rate in a dry soil was initially very large, and we're actually going to solve a problem to show why it's so large. So it says, even though the hydraulic conductivity is low, the capillary pressure gradient, and why is the hydraulic conductivity low in a dry soil? What did we learn about that last time? While you're thinking, I need to go take care of something right here. So why is the infiltration capacity, did I say hydraulic infiltration capacity? Or did I say hydraulic conductivity? What does the book say? Hydraulic conductivity is low in a dry soil. Why? What did we say about that last time? If you're in the unsaturated and saturated zone, what's true about hydraulic conductivity? What's true about hydraulic conductivity in the unsaturated zone that is not an issue in the saturated zone?
Conductivity is less. In the,
It's not only less, what else is true? What's it a function of? Not exactly. I'm sorry.
Function of moisture content.
Exactly. K of theta, right? We didn't use the terminology K of theta in the saturated zone, but what we learned the other day is that in the unsaturated zone, hydraulic conductivity is a function of moisture content. The question is why? And why is it so much lower in drier soils? What's going on in the water, in the soil, with regard to where the water is and how it's behaving? Right? We spent a fair amount of time on this on Wednesday.
Pores filled with like air.
Some of the pores are filled with air. Which pores are filled with air?
the large one.
The bigger ones, right? Those drain first, leaving the water in the finer pores, sometimes with no direct path to connect to other finer pores. So it's much harder for water to move around in an unsaturated soil, particularly if it's confined to the smaller pores, which naturally have slower rates of transport, right? So that's going to be the case, that the hydraulic conductivity will be low in the unsaturated zone in a dry soil. Now, they're going to point out something that's actually quite intriguing, and actually I never really thought about it this way until I read this example in this book. We all know, or we may not know, but you've already seen some examples in graphs that say, initially, when it starts to rain, the infiltration capacity may be quite high, and then it comes down and levels out, right? And so there's many explanations you could come up with for that, right? You're filling up the soil moisture storage. Some people talk about like maybe clay minerals that swell and help to seal off the soil surface. But the reason why it's so high is the interesting question. Why is it so high to begin with? So here's the analysis. If the capillary pressure head 10 millimeters below the surface is initially -2 meters, right? What they want us to do is to calculate the hydraulic gradient. So imagine that I've got a soil surface here and that it's raining enough that the soil surface is completely wet. But the wetting front has not gotten down to 10 millimeters yet. So at the soil surface, if it's completely wet, what's the head? What's the pressure head? Right, you're right at the surface, it's wet, but it's not underwater. So what's the pressure head then?
Should be gauge pressure, right?
Should be gauge pressure, atmospheric pressure, right? You're at the contact between water and the atmosphere, but there's no actual depth of water creating hydrostatic pressure. But so P is 0 here. But 10 millimeters down, you have tension head. And what they're telling you here is that the tension head is minus 2 meters, equivalent of 2 meters of water, but negative pressure, tension, holding whatever moisture is there in the pores. So what's the hydraulic gradient? Well, what's total head? There's two components, right? What are they? Right. So what's the elevation difference between 10 millimeters below the surface and the surface? 10 millimeters, right? Or 0.01 meter, right? So if you think about the hydraulic gradient being dH dz, where H is Z plus psi, where psi is the tension head and Z is the elevation head, right? So in your numerator, you've got, if you're thinking about going from the surface down, then you're at 0.1 millimeters, you're at 10 millimeters, 0.01 meters at the surface, and down below, you're at 0 compared to that. So and then if you say, and then I'm at 0 pressure and I'm subtracting -2, those two sum up to 2.01 meters. So the difference in head is 2.01 meters. But what's the denominator is the difference in Z. What's the difference in Z? 0.01 meter. So if I divide 2.01 by 0.01, I get 201. That's a pretty steep hydraulic gradient, right? That's the derivative of tension head plus Z dz. And so that is a large hydraulic gradient. So now, what does Darcy's law say about how fast the water is actually going to move? You have to know both hydraulic gradient and the hydraulic conductivity, right? So how do you figure out how fast the water is moving under that hydraulic gradient, given that they're telling you you've got a hydraulic conductivity of 10 to the minus 6 meter per second, and you've got a hydraulic gradient of 201. So what's the flow rate? And let's assume that the flow rate now is infiltration down into the soil under that hydraulic gradient with that hydraulic conductivity. How do you calculate that? What operating rule do we have that allows us to calculate that flux rate? It's one we've been talking about for several weeks now. It comes up every class day at length. And I've asked you to draw it on the board several times. In fact, it's on the board right now. Darcy's law, right? Darcy's law. So what does Darcy's law tell you is what do you need to do to figure out how fast that water is moving using Darcy's law?
Hydraulic gradient,
Hydraulic gradient times
K.
K. Okay, so let's calculate it. So let's see if it does that. All right, so DHDZ we've just said is equal to 201, right? That's dimensionless because H and Z are both. So that times K we said is 10 to the minus 6 meters per second, right? So that 10 to the minus 6 times 201 is what? Meters per second, what is that? (2.01 times
And the negative 30.
2.01 times 10 to the minus 6.
Oh, Yes.
Okay, so you say yes, you have to answer the question, Madison.
What? Oh, 201.
201 times 10 to the minus 6, right?
Yes, so. Zero.
Thank you. 2.01 times 10 to the minus 4. All right, so 2.01 times 10 to the minus 4, 2 seconds. You're doing fine. Everybody has, a little rating fees. So now let's translate that into millimeters per hour. So that's 2.01 times 10 to the minus 4th, and is 1,000 millimeters. So it's going to be 2.01. It'll be 0.201 millimeters per second. How many millimeters per hour is that?
I'm sick.
I may have made a mistake here somewhere, but keep going. 60, right? 60.
60.
Oh, you did make a mistake. I do wrong. No, how many seconds are there in an hour?
1,000.
How many seconds are there in an hour? You can do better than that.
1,200.
Hmm?
Yeah, 1,000. Oh, no, sorry, 3,600.
Thank you. 3,600. So 3,600 times 0.201 is how many millimeters per hour?
723.6.
Well, let's just stick with 720. We'll round off, but that's good enough for us because that's what the book. But yes, you're correct. So 720 millimeters per hour. Have you ever seen it rain 720 millimeters per hour? That's like, that's more than 2 feet in an hour, right? So the world record rainfalls actually have gotten in that realm. You remember this curve I showed you with the maximum precipitation ever recorded? There are some examples like that, but they are few and far between. So the bottom line is, that's 720 millimeters per hour. They say it would be quite intense, which is kind of an understatement. Yeah.
That's 2 feet per hour?
Hmm?
That's equivalent to 2 feet per hour?
Well, you can figure it out, right? There's 30 centimeters of the foot, so 60 centimeters would be 2 feet. So 12 more centimeters would be about half a foot, so it's about 2.5 feet.
2.5 feet. That's
2.5 feet of 2.5 feet of rain of infiltration in an hour. The question is, would you ever get that much rainfall? And in the vast majority of cases, the answer is absolutely not. So why is that relevant? Because what it's telling you is that you've got extraordinarily high, in this example, the way they set it up, at the very beginning with that dry soil, you've got extraordinarily high possible infiltration capacities. But by the way, that's largely because we were measuring the head at 10 millimeters below the surface. What happens if the wetting front moves down to, say, 100 millimeters? The hydraulic gradient is 1/10 of that if it's 100 millimeters, right? So as soon as the wetting front moves down, that hydraulic gradient changes and the infiltration capacity will go down, right? All right, so that's what they say. The infiltration rate decreases in time as infiltrating water moistens the surface layers, reduces the gradient and capillary pressure head. Ultimately, the near surface portion of the soil approaches saturation. The capillary pressure head gradient approaches 0, and the infiltration rate will then approach the saturated hydraulic conductivity. And so it says here the infiltration capacity curve for any given soil would depend on the soil properties also. But let's see, do we have, so here is figure 8.9, the one they're talking about. And it's showing you, there's a curve kind of like what we've just been talking about, right? Very high infiltration capacity at the beginning, lower infiltration capacity later, ultimately approaching asymptotically the saturated hydraulic conductivity there. Now, then they have some statements. So I'm just going to kind of read you through what was here in the caption. So when water ponds at the surface, the infiltration rate, this is for the blue curve, starts out at a very high value because of the large downward gradients in capillary pressure head. We just demonstrated that mathematically. And decreases steadily toward the limiting value of saturated hydraulic conductivity. You can see that on the figure. And when water is sprinkled on a soil surface, but here's what's different. Suppose you sprinkle water on a soil surface at a slow rate that does not exceed the initial infiltration capacity. What happens? What's the infiltration rate under those conditions? If the rain rate is not greater than the infiltration capacity, what is the infiltration rate?
It's high.
It's what?
The rain rate?
It's the same as the rain rate because all the water infiltrates, right?
Yeah.
So that's this case right here. Because look here, if it's not raining as hard, as fast as this infiltration, well, no, let me back up. Suppose the infiltration capacity, this is the same soil. So if the initial infiltration capacity is up here and it's raining at this rate, all the water is going to infiltrate. And the only time, but as it infiltrates, gradually, the same things we've been talking about will cause the infiltration capacity to gradually reduce as the hydraulic gradients change. And ultimately, you're going to reach a point where now, all of a sudden, the infiltration capacity drops below the rain rate. And from that point on, you see this curve. So here's the thing. We have a flat curve, constant rain rate, until we reach the point when the surface is either saturated or when it's basically got to a point where the rain rate is no longer less than the infiltration rate, and now you have your curve coming down. Now, we are going to use the green amp method to try to simulate these patterns. But I'll just point out that there are two different representations of the green amp method between the Hornberger book and the Digman book. It's not because Hornberger doesn't know what he's talking about. He's written some of the seminal papers about it. And but the point is that they chose not to go there. So they only talk about a case that looks like this. In other words, the cases that they look at that we're going to work with in the first spreadsheet are essentially assuming that the rain rate is always greater than the infiltration capacity. And so you can watch the infiltration capacity come down. You're not dealing with this case until we get the version of the spreadsheet that is in that comes with the Digman text. Are we doing okay? Does it make sense? Yes? Yes.
So you just said that the rain rate usually exceeds the infiltration.
Well, it doesn't actually. So let's put it this way. It depends on where you live, right? So if you live in a nice forested landscape with deep soils, lots of organic matter, and it's not like packed clay or something, then it takes a very big storm to generate enough water that it actually accumulates to the surface. If you live in my backyard, which was a part of a suburban subdivision where they basically removed most of the topsoil and it was hard packed, almost every time it rains, water runs off the surface because it's got very little infiltration capacity left. And actually, a big part of the problem with urban hydrology is not just that we've got impervious cover, it's also that when we create urban soils, we compact them and we do not preserve the moisture holding capacity. I mean, if there's actually a solution to that big problem, it would be do something about moisture holding capacity of the soil. The problem is most of it's already been ruined anyway, but you know, if you could make we have someone on our campus, Stu Schwartz, who studied this at some length, how to actually add back some soil moisture holding capacity. And he's argued that if developers all preserved more of the soil rather than cutting it off and removing it and then sprinkling a little bit of topsoil on it and some, you know, stuff that makes it grow quickly, we'd have different hydrologic response from a lot of these watersheds. So I forget what you said when I was answering you. I think I didn't cover everything you asked.
Windows.
Okay. Dan, you wanted to say something.
I'm still just a little confused. To me, it sounds like if the rain rate exceeds infiltration, that can cause flooding, but it also depends on how permeable like soil around is.
So this is correct. Let's put it this way. In a natural forest soil that doesn't have bedrock right at the surface and that has, you know, enough organic matter and enough porosity and enough pore space that's actually connected, you'll have pretty high infiltration rates, and it would take an enormous storm to overcome that. And so the vast majority of the time, it would just be like pouring a cup of water into a pile of sand. It would just infiltrate.
Okay.
But if you change the infiltration capacity of the soil by taking away a lot of that, then you're actually going to have a soil that's going to have a lot more runoff because it can't infiltrate because the infiltration capacity has been reduced as a result of the things that we've done.
All right.
Now, if you're in a bare rock environment, you know, if you're out on slick rock out in the Arizona desert, yeah, you're going to get very rapid surface runoff because it's just bare rock in some places. But that's a separate issue. This is going to feed into our discussion of rainfall runoff relationships when we get into the next chapter. But that's the reason why we're covering this chapter first, because you start to see why I said that the soil is the gatekeeper, right? So this actually is just continuing on this theme. So it says the rainfall rate exceeds the hydraulic conductivity of the soil. And if the rainfall persists for long enough, the ability of the soil to infiltrate water will drop below the rainfall rate after the hydraulic gradients of the surface become reduced. So, you know, if this is exceeding the hydraulic conductivity of the soil, in this case, the rain rate is less than the ability of the soil to transmit the water, which is why it all infiltrates. In this case, it's infiltrating, but it's reducing the infiltration capacity as you go along. Now, the time at which this happens right here, when you actually start to see the infiltration rate drop below the rain rate, even if the rain rate is constant, is called the time of ponding. You'll see the time of ponding again when we get to the second spreadsheet. Time of ponding is when you start to get water accumulating at the surface rather than having it all of it infiltrate. And so if they're just explaining the whole thing all over again. So you can read this on your own. This is all right out of the book. Okay. But you get the picture, right? So there have been various attempts to model, to simulate these processes. I'm showing you one that we're not going to actually use, but just to point out that it's one of many, and it's one of the early ones, and it's by one of the most prominent hydrologists, a civil engineer by the name of Robert Horton. I've referred, I think, to his book, to his paper he wrote before, which has many seminal contributions in geomorphology, but he did a lot with surface water hydrology as well. So what he did was to observe that if you kind of look at the shape of these kinds of curves, they look like negative exponential functions. Turns out they don't necessarily all fit negative exponential functions, but he thought that was a good function to try. And so what he did was to basically say, okay, I'm going to create an equation that says that F sub C is the final infiltration capacity. So we're going to say the final infiltration capacity, that value that we're approaching asymptotically, after enough time, this term here goes to 0 because e to the minus kt, as t goes up, e to the minus kt goes to 0. And that therefore, this drops exponentially and eventually flattens out, right? So what is in here? It's the original infiltration capacity minus the final infiltration capacity. It's this amount. So as time goes on, this declines until it approaches the final value. So the virtue of this is that you can actually get infiltration rate measurements, and you can fit negative exponential function to them. And if you get a good fit, then you can actually empirically decide that you'll use that to describe how the infiltration capacity of that soil changes over time. Now, when you actually try to fit, you don't always get the best fits, but nevertheless, it was a good idea. There's quite a few other equations that are used for this purpose. This particular equation, you can probably come up with physical explanations for why it might work, but it's not physically based. It wasn't based on the original physics of the process, right? We already know what is the equation that governs how water is transported in the unsaturated zone. What is that equation? We talked about it on Wednesday, right? We derived the one-dimensional form of it. Anybody remember what that was called? The Richards equation, right? So the Richards equation is the actual more complete version, and you can do a three-dimensional version of it, but we're not going to get too fancy about it here. We're just using the one-dimensional form of the Richards equation. I'm not going to derive it again. We did that on Wednesday. You've seen it. It's in the textbook. It's in the slides. So we're going to talk about the Green-Amp method instead. The Green-Amp method basically is a version of the Richards equation that has been has some simplifying assumptions built into it that make it easier to solve. So it's just like we talked about boundary value problems in terms of groundwater flow, and you can even solve a groundwater flow problem graphically if you're setting the boundary values so that they induce the way you draw your flow net. So here, there's some fundamentals about the Green-Amp method that we're going to explore before we open up the spreadsheet and actually try it ourselves. So it assumes. So I showed you the wetting front, and it wasn't always flat. But the Green-Amp method assumes that essentially you got this much moisture in the soil, and as I add moisture from above, the wetting front just moves vertically downward as a flat surface. We call that plug flow. Okay. It's flat. So there's no dispersion of different depths of that surface. We know that's not strictly realistic, but the question is, can you get away with it as a working assumption? So we'll see how well it works in comparison with the measured data in an example from the book. So if you've got essentially the assumption that you have a horizontal wetting front, and that above the wetting front it's saturated, and below the wetting front it's whatever the ambient moisture content was before it started raining, that's the fundamental assumption of the green ant method. Okay? One of the fundamental assumptions. We also assume there's some antecedent moisture content, we'll call it theta zero. That's the moisture content of the soil before it started raining. The wetting front marks a sharp boundary between saturated conditions above the wetting front, where the moisture content is equal to the porosity. It's just saturated, right? And the antecedent moisture content below the wetting front. So if you look at the figure in the book, which I think will be coming up in a minute, you'll see it's like assuming that if this is saturation and this is the original moisture content, you've got a vertical line down to the wetting front, then a horizontal line, and then a vertical line, and there's just a sharp transition between them. That's the assumption they're making, because it makes the problem tractable and it makes it relatively easy to come up with solutions. We assume that if the surface is saturated, tension head at the surface is zero. We've probably said that 3 times in here already today, right? If the surface is saturated, right, you have a zero tension head, and you also have a zero pressure head because you're right at that surface, right? We further assume, and this is something we haven't talked about yet, there's a constant value of tension head at the wetting front, which we call psi sub f. And that remains the same as the wetting front migrates downward through the soil. That's a fairly big assumption. We don't necessarily know exactly what the tension head is right at the boundary between the saturated zone and the unsaturated soil that's got a certain moisture content that existed before it started raining. But we assume that whatever it is, if we can figure out what it is, we can assume that it stays the same even as the wetting front migrates downward. That makes this problem easier to solve. If you know the wetting front at a depth of the wetting front at a particular time, you can calculate the cumulative volume of water infiltrated up to that time just by multiplying the depth of the wetting front by the percent of the soil soil volume that you added, right? So the difference between saturation and whatever you started with, that's some fraction of the volume. That fraction of volume times the depth will tell you how many millimeters or centimeters or meters of water have actually infiltrated down through that vertical column. So it's going to be L sub F, which is the depth of the wetting front, times delta theta, is going to be that amount of water. It's an equivalent depth of water in the soil column. Okay, so like if delta theta is 0.3 or 30%, and the depth of the wetting front is 1 meter, then 1 meter times 0.3 is 0.3 meters of water. Okay. So in most cases, they say the initial rain rate is less than the infiltration capacity, and all water infiltrates. But that is not what the method we're going to use in the first spreadsheet says. We'll have to deal with that in the second spreadsheet, because the Hornberger textbook did not give you that case to deal with, probably because it's a little more complicated computationally, and they were trying to stick to fairly simple to explain concepts. It's not like they don't know about it, because Hornberger's been the author of some of the seminal papers that are used actually to address this issue.
Wait, so you said, in the Hornberger, net, or in like,
So we're going to develop that right now. You're going to see it.
okay, you said it doesn't include that assumption?
So
right there?
I think I added this statement. This did not come out of the book.
Oh, okay. But,
In fact, I may have written, I don't know if, I may have written this text, although it's based on what you see in the book. But basically, most of the time when it rains, it's not raining faster than the water can infiltrate.
Yeah.
Depending on what kind of soil you're dealing with. So most of the time, that means that all the water will infiltrate until the infiltration capacity comes down. That notwithstanding, the example that the book uses is not assuming that. And that's what I'm going to show you. In fact, all the examples you see in textbooks have what I consider to be pretty high rain rates, which doesn't address most rainfall events. But of course, the rainfall events that create problems are more intense ones, so. I mean, it's not a big story if it rains and it infiltrates. People don't write news articles about that, you know.
I mean, I guess with like increasing the severity of rainfall events.
Well,
It
that,
become a
indeed,
normal-
that's one of the things we're doing research on.
Yeah.
So this follows the development of the equations on page 227 to 229. There's a complete derivation of how you wind up with the final equation we're going to see here. I'm not going to take the time to go through that derivation. I have done it sometimes in the past. I've got 3 pages of notes that walk you step by step, including the steps that the textbook skips in terms of how they actually do the integration to come up with the final equation. But the bottom line is this: there are some fundamental, everything we just talked about as an assumption can be built into fairly simple equations, like the infiltration depth up to some period in time is equal to the product of delta theta, this increase in soil moisture, times the depth of the wetting front, okay? So that is, we're going to see something called capital I, that's the depth of infiltration. The depth of infiltration in terms of the amount of water, not the depth of the wetting front. And down here, the soil is initially dry, so it's got theta sub I to begin with, and you see you've got a sharp wetting front here, right? So that's what we're saying about being horizontal. So the other assumptions built in here are that up at the surface here, that surface is wet and saturated, and therefore the tension head is 0. And down here, they're assuming that there is a unique value of the tension head at the wetting front, we're going to call psi sub f, and that it's the same value no matter where the wetting front is. At any time step as it's moving down, it's assuming that it has the same tension head. Now, this is what I just talked about. Infiltration depth in terms of amount of water is just the product, like, looks like my battery's dead. It's just the product of those two things, delta theta times L sub F. So infiltration depth is equal to this product. Now, there's a bunch of manipulations of some of the governing equations that you have to go through in order to wind up with this final equation. I'll just tell you what this equation is. We're going to work with it very shortly. So you all know what most of these things are. What's that? K sub S. Capital K, what is it?
Not in the
Yeah.
Saturated hydraulic conductivity, right? It's okay. We just talked about this, right? That's the difference in moisture content as you wet the soil. This here is tension head at the wetting front. This here, so actually there's only, all the variables in here you've already seen. This thing here is time. So here's the interesting thing. Do you remember when we did the specific energy diagram and we developed the equations, and we started with a cubic equation, we had to then basically do trial and error to find the water depth corresponding to a given value of specific energy, right? On both limbs of that curve. We couldn't solve for the depth from the specific energy. It was what we call an implicit equation. You couldn't solve for the depth from the specific energy, but what you could do is do trial and error to keep putting in values of depth and seeing what specific energy they gave you. Then you could plot the depth against the specific energy and find what you needed to find. Or you could play with values of the depth to get it to give you the specific energy you needed. This too is an implicit equation. You're not trying to solve for the time. What you want to do is to find the infiltration capacity, the depth of the wetting front, and all those things as a function of time. But when you do the integration of the differential equations here that are governing this, you wind up with time as a function of all these other things. But the thing is, in the spreadsheet or any other numerical method you use, you can solve for the time corresponding to, say, values of the infiltration depth. And from that, you could get all of the different variables and you can plot them against each other and see what the relationships are. So even though it's implicit rather than explicit, it still could give you what you need. So these spreadsheets are structured basically to do that. So you could, this is equation 8.15 in the textbook on page, I think it's on page 227. It says you could program that to derive a relationship between time, infiltration rate, the change in moisture content in the wetting, above the wetting front, cumulative amount of infiltration, and the depth of the wetting front. So we use those to solve for time, but then we have a relationship that allows us to see how they vary with time. And the approach in the Hornberger textbook does not account for that initial period where all rainfall might be infiltrating. They're only developing a curve that starts with a rain rate high enough to give you those high infiltration rates in real time. Okay. So you're going to see in figure 8.9. No, it's the next figure. Assumes rainfall is always greater than infiltration capacity. Now, in fact, infiltration capacity that we've calculated there as an example is always way higher than any real rainfall you're going to get. So most of the time, you will actually have some period where all the water infiltrates, depending on the kind of soil. I mean, if it's paved, then it's mostly going to run off. If it's very low infiltration capacity, then you probably will get runoff pretty quick. And you probably will exceed the infiltration capacity pretty quick. So this is basically a representation of a bunch of measurements using probably something like a double ring infiltrometer over time from a sprinkling experiment, and the cumulative depth of water infiltrated as a result of those experiments. And this is the green amp method used to predict what it will look like. And that's a pretty good fit. This is not a line that was fit through these observations. Okay. This line was developed from the parameters and knowing what the rain rates were. And so the point is that even with those simplifying assumptions, at least in some situations, the green amp does a pretty good job. And so it's often relied on as sort of the preferred, not by everybody, but it's often, a lot of people who do hydrologic modeling would use the green amp method for their infiltration function. Now, I already said this, right? There are versions that handle downward trend. So I didn't show you this yet. Everything we've just said assumes that that surface is saturated and that that plug of moisture, the soil is saturated throughout the depth of that plug, right? There are situations, though, where it's not necessarily saturated, but you still have downward transport in the soil, okay? This method we're going to use doesn't account for that, at least in the form we're doing it. There are versions of the green amp method that can handle downward transport of moisture that's not completely, the soil that's not completely saturated. The Dingman textbook has more varieties of the approach to the green amp method, including less than saturated conditions, including varying hydraulic conductivity rather than one value, and situations where it can even happen if the water table is at fairly shallow depth, and you've got a plug of water migrating downward. It's possible that plug of water meets up with the water table and causes the water table to rise. But that's not incorporated in the approach to the green amp method we're using here. It's not incorporated in the version of the green amp method from Dingman that we're going to see in the other spreadsheet. But if you read Dingman's chapter, he shows you how to account for those other alternatives. It's just that we don't want to take the time to have to go into all those things here, because we're most interested in getting the fundamental concepts down. So this just illustrates another couple of field examples. So this always irritates me. I don't know how to make this thing go away. If I click on it, then retreat. Well, okay. Sometimes it works, sometimes it doesn't, but that's not the figure I want. So this is showing you, there's an example where this is the same soil, this is double the rain rate of that run, but what you're seeing is that there's a wetting front moving downward in the soil, but it's not completely saturated because the moisture content is less. If this is saturated, then this is less saturated. So you can indeed get a wetting front moving downward at a measurable rate at a fairly steady percentage of soil moisture, but it's still not saturated. That's just not a contingency that's covered in the particular version of the equation we're using. But if you become an expert using the green amp method, there are variants that will allow you to do that. So this here shows you what happens if you have essentially a sprinkling experiment or just a rainfall event, and you have a plug of moisture that winds up going down into the soil, and then you just let it drain. You get the vertical redistribution of the moisture. So notice that throughout this stuff, the moisture content reduces, but then some of it drains down to here. So some of this is redistributed from up here to down here. That's after the first 6 hours. After 4 days, you're further getting some of this being reduced. and it's being redistributed down here. And then after 30 days, you can see what's happened, right? Now, there's also probably up here some evapotranspiration removing moisture from the soil, but that's just illustrating some things about the way that under natural circumstances, moisture does redistribute downward. And this shows you again, I think I showed you the version of this figure before, after 0.8 of an hour, after 8 hours, after 83 hours. But notice this is a field picture taken by Dingman himself, I think, after an intense storm. There's a pair of boots for scale. So this is only about, maybe 1.5 feet down. That's a sharp horizontal wetting front. So that proves it does exist in some places in nature, right? I guess they dug the hole after the rain was over. And this just shows you that you have to remember that in the unsaturated zone, the hydraulic conductivity is a function of moisture content. And as you wet the moisture, if you add moisture content, you increase the hydraulic conductivity. And eventually you may get it all the way up to saturated hydraulic conductivity. If you dry it out, it's going to come back down the other way. This again is showing you an example of unsaturated downward flux, a wetting front, because this is porosity. So if we're saturated, the value, this would be all right over to here. But in fact, physically, you have a downward motion of the wetting front, but the soil is not completely saturated. How's that physically possible? I mean, is there anything not logically possible about that scenario? Other than the fact that I only explained it in the context of it being completely saturated?
It's possible.
Yeah, because if it's not raining that hard, you're not adding that much moisture to the soil, but you add enough that the hydraulic conductivity is just enough to transport that downward without having a higher moisture content. That's a real case. You can solve for that. We're just not doing it here. And this just again shows you conceptual. So it says successive water content profiles at varying depths at different times. And this is showing you what's happened to the infiltration rate at different time steps as that's going on. The time of ponding, I think, is this one right here. Don't ask me why, but I think that's just the depth of the wetting front when you happen to reach the time of ponding up here. Oh, I know. So if this is the time of pond, I'm not sure. I'm forgetting what ZF of T sub P is because I haven't looked at the full duration in the textbook recently. So these are just other examples that are computed with the green and amp method, but I'm going to skip ahead from this now. We're not going to do this. We're going to switch to the first spreadsheet. So if you need to go take a bathroom break or something, go ahead and do that. But have the first spreadsheet on your desktop, and we'll start talking about it in a couple of minutes. It's this one here. Oh, that's not the version. That's one I already saw. Let me go get the one that's not. Okay. Oh, I thought I undid that. Okay, it should look more or less like this. I'm thinking drink of water. We're going to stop in about half an hour because I have to go for another interview. So we'll have to continue with this on Monday, but at least see how it works with the one spreadsheet today, and maybe have time to pull up the other one and look at it briefly. So those of you who are actually in here, if you pull up the spreadsheet and open it, you can actually start to explore by looking at these different columns. and looking at the formulas. So what I'll do when everybody's back in here is we'll talk about what's in each column. But time, remember, is going to be calculated from this equation, which is the same one we just showed you. We are going to start by assuming different total amounts of infiltration, starting with very, very little and increasing to more and more. And we presume that that is going to develop through time. And once we know these values, we can figure out the depth of the wetting front, we can figure out the time, and we can also figure out the infiltration rate. So I'll show you how that works. Then we'll develop some of the curves that illustrate the results that you get. And we can develop the curves that are exactly the same ones that are in the textbook. For figures 8.9 and then also for figure 8.11. I've got a separate tab for that. Did I give it to you, Phil, or did you fill it yourself? I didn't, or I did? Okay, erase that. Everything but the first line. Don't erase this line here, but erase the other lines, because I thought I'd uploaded a version that didn't have all that stuff in it. But I guess I was mistaken. Because you want to see how to actually develop it, not just look at what I gave you. So one thing I'll point to while we're waiting for others to come back is you want to keep in mind the infiltration rate in the zone that's moving downward like this is still following Darcy's law. So it's still going to be the product of the set of the hydraulic conductivity, which if it's saturated is the saturated hydraulic conductivity, times the hydraulic gradient. And hydraulic gradient is going to be psi plus is going to be the difference in psi plus z over the distance z. The distance z here is the same as the depth of the wetting front between here and here. So the change in psi is the change between 0 here and psi sub f here, right? So if delta z is L sub f, right, and delta psi is 0 up there minus psi sub f down here, then you can actually develop a formula. If we actually go back to the textbook, I've got it in there. Okay. So this is just a reminder that when you look at the spreadsheet, some of the things that are in it are really just a version of Darcy's law. So if you look at, this thing's about dead, so it's gonna work. Let's see. So if you want to calculate using Darcy's law, the rate of downward transport, the infiltration rate, we're going to assume the infiltration rate, if this area is saturated, is going to be the same as the specific discharge in the downward direction that we got from Darcy's law, right? So that's just the product of the hydraulic conductivity times the hydraulic gradient. So hydraulic conductivity is going to be K sub S. The hydraulic gradient is going to be the difference in the head between here and here divided by the distance in Z between here and here. The distance in Z is just the depth of the wetting front, so that's going to be the denominator. the difference in the hydraulic gradient, the difference in the hydraulic head is going to be the head up here minus the head here. Okay, so let's take a look at the equations that are developed from that. And actually, if we just scroll down in the textbook here, you'll see what they do. So they say, the hydraulic gradient is up here. It's just elevation plus 0. There's the pressure head is 0. Down here, it's psi sub f, right? So actually, it's elevation plus L sub f. It's a psi negative psi sub f because it's this minus this. And so if you take the difference between here and here, you'll get negative psi sub f plus L sub f, and dz is just L sub f. And if you go down to this equation, you'll see that's how they've written it. Negative psi sub f plus L sub f is the difference in head between the saturated surface and the bottom of the wetting front, and L sub f is just the depth of the wetting front. So that ratio is the hydraulic gradient. So that formula for infiltration is actually a form of Darcy's law in one dimension, which means that when you go over here to this spreadsheet, you'll see I is equal to exactly that. That's the equation that I just showed you. So this is a form of Darcy's law used to predict the infiltration rate here. Same time, if you go over here, we're just assuming different depths of the amount of water, different amounts of water having infiltrated. Presuming that as more infiltration goes on over time, that amount increases, right? And you can get the depth of the wetting front because we know that infiltration rate is the product of the depth of the wetting front by times delta theta. So if you know the depth of the wetting front, not the depth of the wetting front, if you know the amount of infiltration, cumulative infiltration, you divide it by delta theta and you'll get the depth of the wetting front. So if you look in the formulas here, this is what I want you to do. So make sure you can recreate these formulas. So here's how I'm going to do it. I'm going to basically recreate these formulas in real time so that you can do the same thing just following along with me. I'll probably make a couple of mistakes because it's almost impossible to avoid doing them in this context. But so I'm going to make this 0.0001 zeros, just so that we are basically solving the same problem as we got in the first line, and we'll see if we got it right by knowing if our answers match up, right? So to get the value of the depth of the wetting front, what do? You take this and you divide it by delta theta. So if you look here, I've highlighted in yellow a bunch of the parameter values that we're using. So for this example, which is actually the example in figure 8.9 in the textbook, they tell you that hydraulic conductivity is 7 times 10 to the minus 6 meters per second. But since they graph it in terms of meters per hour, all I did was multiply. I basically, how many seconds in an hour, if you multiply that by 3,600, you'll get this value for meters per hour. Okay. So in the formulas, wherever I need K sub S, I'm going to use this. And wherever I need delta theta, I'm going to use this, because that's delta theta right there. And if I need the tension head at the wetting front, I'm going to use this. So they gave us those values. They said, use this for tension head at the wetting front, use this for delta theta, and use this for hydraulic conductivity, which turns into this if you make it into meters per hour. So you plug those in, it's really not that hard to solve this problem if you're given those parameters. So let's start by saying, okay, right here, I'm going to say equals the value of cumulative infiltration divided by delta theta, which is up here, but I'm going to make it an absolute cell reference. So I'm going to hit function F4 so that when I copy that down, it's still going to go back to that cell to find that constant. And indeed, I get the same value because I'm using the same value of I. Similarly, if I go over here, now I want to calculate the infiltration rate. So I'm going to say equals negative K sub S. So negative, well, actually, it says use K sub S instead of negative. So we're just going to use K sub S. So equals K sub S. That's over here. See where I wrote use this? That's what you should use for K sub S. So I'm going to use this absolute cell reference times, open parentheses, negative psi plus psi sub f, that's this. So I think what I'm going to do is open parentheses for the numerator and divide that by the denominator. So I'm going to say equals negative of this, and I'm going to again, make it an absolute cell reference, plus L sub F, which is actually over here. We just calculated it, right? So I'm going to close parentheses and then divide again by L sub F, which again is here. And if I hit return, I should get the same value, and I do. Right? And you did too. And yes, what's your question?
I got 0.23.
There's
you
probably
you
either
made
a missing
copy.
parenthesis or something
Okay.
like that. That always trips people up, trips me up all the time.
You made a copy. That's my bad.
So, so this worked. So now this is the more challenging one. Once we calculate this, so here, once we got this in meters per hour, we can turn it into millimeters per minute if we want, right? How many millimeters in a meter? 1,000, right? So you multiply by 1,000 to get the number of millimeters per hour. If you want to know the number of millimeters per minute, what do?
1,000 divided by.
Yeah. So let's do that. We're gonna say this equals this. Whoops, not that. Equals this times 1,000 divided by 60. And indeed, I got the same value. Okay. So this is the one that's a little more complicated. It's hard to do this without making some mistakes. So this one has a couple different terms in it. So we're going to start with just I over K sub S. So I is going to be over here. K sub S is going to be over here, right? So we're going to say equals I over here on the left plus, and I want K sub S to be an absolute cell reference because it's only in one cell if I move the formula. So I'm going to hit function F4 there. So that's the first term. And then the second term is plus, now we want psi sub F. So we're going to say psi sub F is right here. I'm going to make that an absolute cell reference. Times, and then I'm going to say delta theta over K sub S. I'm going to put that in parentheses. So I'm going to say that times, open parentheses, delta theta, which is over here, make that an absolute cell reference, divided by K sub S, that's over here, I'll make that an absolute cell reference. Close parentheses. And now I'm going to multiply it by log base E, or what we all know as natural log. So times ln of, and what you see here is it's 1 plus I, I'm going to use this here, divided by, in parentheses, negative psi sub F. So it's going to be negative this absolute cell reference F4 times delta theta close parentheses. Let's see if I have the right number of parentheses before I hit return. So this is times this, natural log of this, 1 plus this over this. That should do it. No, there's a second parenthesis because it's all inside the natural log. Let's see if that solves it. Ah, I got a different number, so I must have done something wrong. So let's see what's wrong here. So B20, that's correct. Ah, but you know what? I didn't multiply. I added it to K sub S. So it's got to be times. I just hit the wrong character. Oh no, it's divided by, not multiplied by. Divided by K sub S. Now let's see what we get. And I got the right answer. Okay. That's just one of those things you got to know how to look for your own errors and fix them, right? So now this we're just going to take in minutes. This is T in hours, so T in minutes, just multiply by 60, right? So we're going to say this times 60. It turns out we're going to plot it in minutes, not in hours. Okay. Now, I'm going to change this back to the original value that I had. now I know that my formulas are right, the way I've drawn them. So I'm gonna make this, instead of 0.00001, I'm gonna make it 0.0001. 3 zeros instead of 4. And right away, you'll see I get different results. More importantly, I can copy this formula down to the bottom of the page. And now I'll start to see the trends up. Right? So all of a sudden, now what you see is, first of all, if I go to the textbook, that is the curve. No, that's 8.11. Where's 8.9? Oh, you know what? That's not the textbook. That's my here. That's 8.11. Where's 8.9? Oh, that's 8.9. So actually, okay, we're trying to replicate the infiltration capacity curve. I thought there was another one here somewhere. Actually, I think this is the right one. This figure represents those same parameters. Here they fitted it to the absolute measurements. This goes out to 35 minutes. And actually, I think this is set the same way. No, that goes out to 80 minutes. So, oh, you know what? Well, whatever it is, I don't remember whether it exactly matches that figure. I thought it did, but in any case, you can see now what you've gotten when you look at these three figures, right? But basically, once we have time, then we can look at the depth of the wetting front as a function of time as it's migrating downward, and it gets down to about 1.1 meters. We can look at the total depth of water infiltrated. That's less than 0.045 meters, but when you consider that it went down over about a meter, the delta theta was only 0.04, that's about right, right? Total amount of water that infiltrated. And over here, the infiltration rate is doing exactly what we would expect. You're starting with a very high infiltration rate. That's about 1.8 millimeters per minute. 1.8 millimeters per minute is a little bit less than 120 millimeters per hour. No, 60 times 1.8 would be, yeah, it's about 120 millimeters per hour, which is pretty unusual around here. You don't get that. But in any case, you see the sharp decline and then it kind of flattens out exactly like we expected it would. So we didn't fit a negative exponential curve there. We developed a physically based simulation and we got an infiltration capacity curve or an infiltration rate curve that seems to kind of match up with what we thought we were going to get. Now, over here, there's another such problem that is set up more or less the same way, except with different values. And it's to match this problem in this figure in the textbook. I guess, is that 8.11? That's 35 minutes. I'm a little confused because I thought I had this right, but these are the parameter values in here. So this would be something we'd have to calculate. I'm not going to do this in here, but you now know what the formulas look like, and it would be entirely possible. Actually, the formulas are right here, right? So those are the right same formulas. Let's make it orange. Right? And so if I want to make, say 0.004, let's say, then 0.001, 0.002, 0.004. I'm just making these up. I don't know how it's going to come out. 0.008, 0.01. Let's see what we get if we just copy those down. These are based on different parameter values, but the equations are the same. And the time in minutes is still only about 2 minutes. So clearly I need to go farther. So let's make this 0.02, 0.05, 0.1, 0.2. All right, so now this goes out to 35 minutes, and I hit 35 minutes somewhere in between here. So instead of using 0.2 here, instead of using 0.1, I'll make it 0.06. And that goes to a little over 35 minutes. So if I do that and get rid of this thing here, I get the curves, right? So there's the depth of the wetting front. There's the depth of water infiltrated. Looks like I probably could have made this a little less bumpy by putting some numbers closer together. And out here, I get the infiltration rate curve. This actually is what you see, I think, in figure 8.11. So if we were to match those up, I think you'd be looking at the same values. About a little under 60, except I was looking at meters. So 0.06 is about 60 millimeters, right? So even though I'm using millimeters instead of meters, it is about the same. It is, we did generate the same curve, okay? Right, so what that basically means is you can use this and say, all right, so what happens if I change the hydraulic conductivity? What happens if I change the delta theta? What happens if I change the value of tension head at the wetting front? How does that alter the infiltration properties of what's going on here? You know, now you'll notice, was there a rain rate in this problem anywhere? No. Why? Because they just assume the rain rate is high enough to generate these rates of infiltration. That's what's different in the Digman. In the Digman spreadsheet, explicitly, you're actually comparing the rain rate. And in the Digman spreadsheet, the first thing you do is to calculate the time of ponding, because all your calculations depend on what happens after the time of ponding. Before the time of ponding, the spreadsheet just assumes that you've got a constant, you know, if it's a constant rain rate, you've got a constant infiltration rate, which is the rain rate. So the only interesting things happen after you hit the time of ponding, and that it's set up a different way. So since I'm going to have to leave in about 8 minutes, I'd suggest let's just go over there and just look at how it's set up. I don't think we have time to actually develop a result. And then we'll finish this off on Monday and talk about some other things. So go to this other spreadsheet. Oops, sorry. It won't have all the things that I stuck on here with arrows and symbols, but this is actually a spreadsheet that comes with the Digman textbook. And so he's using slightly different nomenclature, but let me just show you what he's built into this spreadsheet. Up here, you've got porosity, so that's the same thing as the saturated, as the saturation moisture content. Over here, you've got the initial moisture contents. So saturation minus initial moisture content, that's our delta theta, that's calculated right here. Where is it? They may not have calculated it directly, separately. They may have multiplied it by this here. But once you've got theta zero and you've got the saturation amount, you can calculate the difference between them and build that into your equation. Similarly, they give you, actually, I had a whole recording that I developed using this spreadsheet, and I used it in the earlier class. We don't have time to listen to it right now, so I'll talk about this a little bit on Monday. But I'm just going to show you some things that are in here. So saturated hydraulic conductivity, you can give it a value in centimeters per hour, and then you'll be doing calculations based on centimeters per hour. Now, they don't give you a value for tension head at the wetting front. In the Hornberger textbook, they're just assuming they're giving it to you. What it says in the Digman textbook is, we don't necessarily know exactly what the tension head is at the wetting front, but one thing we can say for different soils is that we've got tabulated values of the air entry tension. That's basically when you have a certain amount of moisture in the capillary fringe that's being held under tension. Different kinds of soils will have different heights to which the capillary fringe will rise. There's tabulated values of the air entry tension. And there's a paper by Clapp and Hornberger, actually, that gives you a formula for figuring out what the tension head is at the wetting front based on knowing the air entry tension. So they basically have you put this in. That's going to be a given, where you look it up in the table. And then the table will also give you values of B. And I'll show you that on Monday. Because we didn't actually do any of this in class today, except just list some of the recording. But essentially, once you've got these parameters, the other thing that's different is it's actually asking, what's the rain rate? And how long does the rain last? And it's just saying, okay, I got a constant rain rate, say 1.5 centimeters per hour for 3 hours. So it'll multiply those two together and give you the total number of centimeters of rain. But the point is, it's going to use that to figure out, based on what it knows about the hydraulics of the soil, how long it takes to reach the time of ponding. That was not at all in the other version of the spreadsheet. So there's a formula up here for the time of ponding, and I'm not going to derive it, but most of what's in here you've seen already. Saturated hydraulic conductivity, tension head at the wetting front, the delta theta, which is written here as porosity minus initial soil moisture. And then this here is rain rate times the difference between rain rate and saturated hydraulic conductivity. You'd have to actually go through the derivation of that formula in Dingman to see exactly how that form got developed, but the terms kind of make sense that they're relevant,
What's
right?
K sat again?
Saturated hydraulic conductivity.
Okay.
K sat is the same thing as we've been calling K sub S. So basically, you got a formula for saturated hydraulic conductivity, and the way this thing works, and you also got, so the way this thing works is in here, you'll calculate the time of ponding, and then down here, you'll put entries before and after the time of ponding. It's just going to be, the infiltration rate will be equal to the rain rate until you hit the time of ponding, and from then on, you're going to develop new values. And so that will give you that flat and then descending curve that we talked about already. But it would take more time than we have to actually develop all of this. I'll just simply point out, I did throw in on here, on this version, it doesn't seem to be the one that I gave you to download. So maybe I should put this up. It shows you that the columns here have cumulative infiltration as a function of time. That was our first column in the other spreadsheet. The infiltration rate as a function of time, which we have a formula for already. That was this here. Okay. It has the depth of the wetting front, which is just this divided by delta theta. You see that here. It has the time. So time is an implicit function of this, except now it's a little bit different because they're saying cumulative infiltration minus the cumulative infiltration at the time of ponding. So this formula depends on knowing what has happened since the time of ponding is reached. That's a fundamental difference in terms of how it draws the curves. But those are details. It's using all the same physics. And so as a result, even though there's some slightly different things in here, and you have to build the time of ponding into this equation, it will develop the curve that looks just like that second curve we were looking at. You know, we were looking at this thing here. Right, so the first one in the Hornberger textbook, we developed a curve that looks like this. The one in the Dingwood textbook, we can develop curves that look like this. Okay. So that's all I'm going to do because we're just about out of time. Does anybody have any questions before we break? Well, then have a good weekend. I will see you on Monday morning. I have to go to my next interview.